Okay, so again, welcome everyone to the next talk in our Engineering Digital Twins community seminar series. Well, if you've seen some of our talks, you probably know the setting. You know the EDT community. You know that we have these bi-weekly meetings. Before going into the today's talk, I would just like to briefly give you some outline, because we are all in this community of engineering digital twins. So I wanted to give you also some overview on where you could publish your results or your research results on engineering digital twins next. So just an outline of some upcoming deadlines. There is for new research results, there is this workshop on formal methods for digital twins and the formal methods conference, where the deadline it's mid of January. Also mid or beginning of January, there are two interesting tracks in the Unseen conference, and there will be also a special issue on engineering dependable digital twins in the simulation journal, where the deadline is February 15th. So it has been already extended. I think that's quite fixed. So deadline for your more mature work could be, for example, this special issue in the simulation journal. But with that being said, let's switch back to the current seminar series, where today we have to talk by Vinay. And in 2 weeks, just to do some advertisement, we will have another talk by Nelly Bencomo. And then 2 weeks after that, we will have, as always, at the end of the series, we will have a panel discussion. This time including speakers from this series, but also including speakers from the previous series. So with that being said, let me introduce Vinay Kulkarni, our today's speaker, who will be talking about enterprise digital twins. Vinay, he's a distinguished chief scientist at Tata Consultancy Services, but also associated with the Indian National Academy of Engineering, and also visiting professor at several British and Indian universities. And his current work, or currently he's working on supporting dynamic adaptation of enterprises using digital twins. We're using different techniques such as modeling, artificial intelligence, but also control theory. And based on this work today, he will be talking about enterprise digital twins. And well, with that being said, Vinay, I'll give the floor to you.
Thank you very much. Let me try to share the screen, or will you stop sharing, please?
Yes, I did, and I can see a screen already.
Okay, great. I'm just need some help. How do I get those right side things out? Because it is consuming a lot of the digital estate.
Yes,
okay, hide thumbnail. I think this is better. Yeah.
Okay, perfect. We cannot see them, but yeah, perfect.
Yes,
if it works.
I think now it's fine.
Perfect.
So, may I start, please?
Yes, sure. Floor is yours.
Great.
Take it away.
Yeah, thanks. Hi, everybody. Good evening. I'm going to give you a whistle-stop tour of Enterprise Digital Twin. It's our attempt at preparing for an uncertain world. So, here is briefly an agenda. First of all, I will introduce sketchily what is an enterprise digital twin. Then I will motivate why there is an increasing interest in this concept. Then I will give a brief introduction to the technology that we have developed to support this concept for a specific set of problems. Then apologies for singing our own praises, but I will briefly talk about the impact which we have created on ground in real world industry scale problems. And I will conclude with open challenges, and there are several of them. So with that, let me give you a brief intuitive introduction to what is an enterprise digital twin. I will juxtapose it with the concept of a digital twin, which we are more familiar with. For example, if you have a reality which is governed by laws of physics, chemistry, and thermodynamics, and you have a bunch of sensors which are looking for which are measuring the relevant parameters of the real life system, then a digital twin is typically a precise mathematical representation of the reality, which is initiated with and kept in sync with the reality through these sensors. And such a digital twin typically has been used to ensure product as well as process quality in a dynamic environment. Now, with juxtaposed with that, an enterprise digital twin, it is also a virtual representation of a reality, but that reality is not governed by physical laws. You don't know all that needs to be known of the reality. So you have partial information. The reality is highly dynamic. And because you have partial information, and probably because the reality is inherently so, the specification of that reality ends up being stochastic. And that's your way of addressing uncertainty, either inherent or due to the partial information. So a digital twin is a virtual simulatable representation of the reality, and the digital twin is kept in sync with the reality uh, using some data transfer mechanisms which need not be instantaneous. They could be epoch based. So the reality where this kind of perspective holds true, at least in our experience, uh, comes in three flavors. They are either businesses like a telecoms company or an insurance company or a banking company, which deals largely with information. So it's an information only space, or it's a cyber physical space. Like you have uh, a reality which deals largely with information, but also makes use of physical entities. For example, a retail supply chain, or let's say a sorting terminal of a packaging industry. And the third reality is a societal space or socio-econo space, wherein you are trying to model a world comprising of humans, peoples, places, and whatnot. So that's what we call it as a space for enterprise digital twin. So with that as a very brief introduction, let me get into the our motivation for this concept. So I think almost everybody on the call over here is familiar with this view of a typical enterprise. It comprises of three layers, the topmost being a strategy layer, wherein the CXX management defines the goals for the enterprise and the strategies for achieving those goals. The layer beneath the strategy layer is the layer of operational processes, which come into existence in order to operationalize those strategies so as to achieve the goal. And the bottommost layer of software systems or systems and software systems uh, comes into existence largely to automate these operational processes. Now, not so long ago, enterprise used to be seen as an island with well-defined objectives that it catered to meet, and the enterprise witnessed fairly low dynamics. So from a control theory point of view, it is an open loop system wherein the knowledge about the goals and about the information that you need to have so as to meet those goals is fixed and fully known. The environment into which this system operates is largely static. The goals that it tries to achieve are fixed. And then all it depends is you now need to define a transfer function which takes the expected set of inputs so as to produce the expected set of outputs, which will then be necessary and sufficient to meet the goals. So it's an open loop system. All that you need to do is spend enough time, design the transfer function, and then reap the benefits as long as the system is useful. Unfortunately, that point of view is no longer valid. Now, what we are witnessing is enterprises are fast becoming an hyper-connected ecosystem that needs to operate in a dynamic and uncertain environment wherein the nature as well as the number of changes are unforeseeable. And it still needs to deliver the stated goals, which, by the way, may change over time in a shrinking window of opportunity. So to meet this in this new scenario, the system cannot be an open loop system. It needs to be an adaptive system. Moreover, it needs to be a learning system. The essential difference between adaptive system and learning system, as we put it, is in an adaptive system, we have the knowledge which we are dealing with remains fixed. And in the light of that knowledge, we try to do the best we can, even if the goals change over a period of time. On the other hand, a learning system helps you deal with evolving knowledge. So learning system has a component which helps you learn the new knowledge and deal with it. So all of you must be aware of the known knowns and known unknowns kind of 4 quadrants. So adaptive system does well for known knowns and known unknowns. The learning system is required to deal with unknown knowns. Unknown unknowns, obviously, we don't have good handle on dealing that scenario yet. So if enterprises now need to follow this path from an open loop system to optimal system to adaptive system to a learning system, one of the key problems that enterprises need to address is that of evidence-backed decision making in the face of uncertainty. So now let's take a look at how the situation is, what is the current state today. So as we just now mentioned a while ago, enterprise can be viewed as a transfer function, which is taking a set of inputs, giving you a set of outputs. And that transfer function was designed to meet certain goals. And if the system is meeting those goals, nothing needs to be done. But if the system is not meeting those goals, either because there is a change in environment, or maybe the transfer function is not correct and some sort of an interventions need to be introduced, then you need a sense and making sense step, which typically is performed by a knowledgeable expert, which looks at the current output, how the current output is deviant from the expected output so as to meet the goals. It's also aware of any changes that have taken place in the environment, and using these 3 things as input, it arrives at the right interventions that need to be introduced into the system. Now, broadly speaking, this is a multivariate optimization problem. And if the system is amenable for completely analytical or mathematical specification, then it can be posed as a multivariate optimization problem, and it can be solved using many techniques like linear programming, integer programming, and whatnot. However, the kind of systems which we want to address using enterprise digital twin, they are not amenable for purely mathematical specification. So purely mathematics based rigorous techniques cannot be applied. The second technique is, okay, if the system is too large, I don't know the behavior of the system fully, I cannot express it in purely mathematical terms, then I will try to learn a model of the system based upon how the system has behaved so far. So we look at the past data of the system, which is a result of the way the system has performed. So in other words, past data is analogous to the behaviors of the system that have manifest so far. Now, we can use recent advances in machine learning to learn a model from this past data and use that model as a proxy of the reality for predictive analysis. Now, this works beautifully well as long as two axioms hold. The first axiom is the data that you have seen so far captures all possible behaviors of the system. And second, future is linearly extrapolatable from the present. Now, nobody knows whether the data that we have seen so far is complete, is capturing all possible behaviors. Therefore, the model which we learned, and even if we learn the model perfectly accurately based upon the data, that model is likely to be a subset of the actual model. And if we use this subset model, even if the future is linearly extrapolatable from past or present, still the analysis is likely to be suboptimal. And because the future may not be linearly extrapolatable, the analysis could even lead to incorrect results. So therefore, the third approach which typically practitioners rely on is rely on human experts. And human experts generally are able to do well the task of identifying the right interventions, making sense of why the output is the way it is, and what needs to be done so as to correct the output in their localized domain of expertise. However, many a times experts find it difficult to justify why have they chosen a particular choice over the another. Plus, we are talking of systems which are large, complex system of systems, wherein each system may have parts which needs deep expertise. So we need many experts, and moreover, which itself is a difficult task, but more importantly, an expert is able to give us an intervention which is correct only for that locality. Expert has no clue what will happen to the rest of the system if this intervention is introduced into the locality. In other words, repercussions of a solution that may lead to local optimality globally, the global repercussions are impossible to fathom. So thus, it can be said that decision making for large complex system of systems, especially when operating in a dynamic and uncertain environment, is a relatively unsolved problem. So the intuition now, what we would like to have is as follows. So when you say that the system has goals, the goal is not just a singleton goal. It can be broken down into sub goals, as you see over here. And those goals may even interfere. The plus sign means it's a constructive interference, meaning achieving a particular goal helps you achieve the other goal. And the minus sign indicates destructive interference, means if you try to achieve a goal, one goal, then the related goal with which it is interfering, you might not be able to achieve it to the desired degree. So thus leading to the notion of a trade-offs. So you break it down your goals to the finest level of goals till that goal can be expressed as an objective function over observable variables, which are your measures. And if the measures are meeting the goals, then the job is done. But if the measures are not meeting the goals, then we now need to introduce some changes, which can broadly be viewed as control variables. And those control variables, when you bring about some change into the control variables, it brings about commensurate change in one or many measures, as is shown in the in the picture over there. So the name of the game is you keep on tweaking these levers, applying these levers in the right sequence till you get the right measures in the right value space so that your goals can be satisfied. So conceptual model for decision making, therefore, is here in front of you, wherein we are saying that system is essentially a transfer function, which is mapping input to output. Environment may influence input. A system is related to other systems either through composition or collection. Composition means you are getting, it's a hierarchical composition. Collection is a flat kind of a composition. System has goals. Goals can be related to other goals through either dependence or constructive and destructive interference. Goal is an objective function which is either a computable expression onto the value space, which is output, or it is some sort of a pattern involving linear temporal logic onto the execution trace of the output. So that's broadly a conceptual model, and it can be supported by an actor-based model, wherein you visualize system as a set of actors. Environment comprises of rest of the system barring the actor under consideration. Actor has goals, actor has state, actor listens to events, actor has a set of actions, and it performs one of those actions when it in response to a particular event. An action makes a state change. Goal is an objective function onto the state, etc., etc. So this model is one of the implementations of the conceptual model, as you've seen earlier. Now, what we have done is we have come up with an abstraction called digital twin or enterprise digital twin, which essentially borrows proven results from the world of modeling and simulation, artificial intelligence and control theory, and builds further upon them. From the world of modeling and simulation, we borrow the idea of a digital twin, which can be glibly seen as a model which is learnable from the past data, that is behavior of the system, plus art of the possible. So art of the possible is where the domain knowledge comes into picture, wherein we say that even though the system hasn't exhibited this behavior, I do know that the system is capable of exhibiting this behavior. So thus together is the system behavior, which we specify using a language. I will touch upon that in a moment. From the world of artificial intelligence, we leverage machine learning so as to construct the model, and reinforcement learning so as to learn what to do when, as a means of introducing interventions, which intervention to use, and what is the sequence of interventions that we need to introduce. And the third pillar is that of control theory, wherein we bring together the real system, the digital twin, and the reinforcement learning agent, all three of them together in an architecture to support continuous adaptation. So control theory offers many variants of adaptation architectures. We focus on model reference adaptive control paradigm. So with these three as together, we have come up with a simulation-based, learning-aided, evidence-backed approach to decision making. And what are the key value adds that the digital twin brings? First, it allows you to recreate the current state in silico so as to explain why it is so in a data-driven manner. Going forward, the digital twin acts as a proxy of the reality so that you can understand response to a perturbation either in the input or in the environment in silico. And a subject matter expert can then interpret, analyze this response to figure out if any intervention is required and what could the intervention be. If a subject matter expert comes up with a set of interventions as candidate interventions, which of these candidate interventions would be the most appropriate can also be determined through simulation. The third value add is as a design aid. So with armed with an enterprise digital twin, you can boldly go where you have never been before, so as to identify if there is a better state possible modulo a certain non-negotiable constraints. Having identified such a state, the digital twin can also help you arrive at a transformative path from the current state to the desired state with a priori assertions. So these are the four key value adds that are possible if you have such a digital twin at your disposal. And some of the concrete benefits which we have realized so far, let me touch upon them. So first is as a experimentation aid. Now, a digital twin can serve as a proxy of the reality. You subject the digital twin to the desired set of inputs that the system is subjectable to for a given time epoch, and you look at the simulated output. Subject matter expert then interprets this output, figures out if what kind of interventions are necessary so as to nudge the output in the right direction. Those interventions can be viewed as sort of a control variables, or these are the actions which you are introducing into the system. And through an iterate till saturate process, subject matter expert arrives at the right set of interventions, which is a significant value add, because now you don't need to design a set of experiments, create a sandbox environment in reality, and conduct those set of experiments with the real system into that sandbox environment, which is a time, effort, cost, and intellect intensive endeavor. Now, everything can be done in silico, or pragmatically, many of the not so good strategies can be eliminated, and only the strategies which seem really well worth can now be simulated for on the real system using A/B testing and some such approaches. But over here, the entire intellectual heavy lifting is being done by the human expert. In order to reduce this analytics and synthesis burden on the human expert, we introduce reinforcement learning agent. So this reinforcement learning agent treats the digital twin as an environment. The desired goal leads to the right reward function. The action space is the changes which the set of candidate changes that can be introduced into the system. And now a reinforcement learning agent will do the necessary exploration with the values of gamma and beta, whatever you want to do, so as to strike a balance between exploration and exploitation. So that's it now leads to a policy, that is the sequence of interventions that will lead to the system reaching the desired state. So with that, let me again give you a 40,000 feet overview of the implementation technology. So what we have seen so far is a notion of a digital twin, and a digital twin is a simulatable model. We want to realize it using actor-based paradigm. So what we have is a language. It's called enterprise simulation language. It is essentially based upon Gul Agha's notion of an actor. So an actor is a purely asynchronous, fully data hiding kind of an abstraction, which is autonomous. It has goals and it knows how to achieve those goals in a proactive manner. And it listens to the events that are taking place in its environment and responds in a manner so as to achieve its goals. And in order to achieve its goals, it may take help from other actor, and it does so by sending a message to the other actor so that the actor does something on its behalf, so to say. So that's the broad idea of actor model of computation. So actor can be viewed, actor has a state, which is nothing but a set of attributes, much like any object, and it has a behavior. So the behavior we specify, like on a particular event, if a condition is satisfied, the condition is a conditional expression on state, then it performs some action. So that is a fully deterministic actor. A stochastic actor is, instead of performing just one action, it offers a probabilistic offers a set of actions with a probabilistic distribution over them, and the simulator then performs these actions in a manner that this probability distribution is honored. Actions are of various types. You can either the change of your local state, or you send a message to some other actor, or you create a new actor, or you just become some other actor. Message is nothing but you raise an event and pass the relevant data so that the event can be handled by someone else. So the notion over here is my system is too large. I don't know the behavior of the overall system, or it is not knowable a priori, but I do know that the system comprises of parts. This is how the parts interact with each other, and the behavior of that part is expressed as an actor. And because I don't know enough about the part, or even about the part, or there could be inherent uncertainty about the behavior of the part, the behavior of that actor is stochastic. That's the idea. Now, these actors themselves can be seen to exist along these three dimensions on a large continuum. So on one dimension, at one end, you have fully deterministic actors. So on event and condition, you perform one specific action. That's it. On the other extreme is fully stochastic actors, as we discussed just now. The second dimension is either you have full knowledge about an actor, or you have no knowledge about the actor. If you have no knowledge about the actor, then its behavior is likely to be stochastic. If you have complete knowledge, then its behavior is likely to be fully deterministic. The third dimension is that of rationality. So the rational actor is an actor which honors its specification, and a random actor is it does something which is not specified or specifiable. So far we have supported all 5 kinds of actors except the random actor. So let me now get into the nature of problems that we have solved using this abstraction. So the problems are decision making and dynamic adaptation. So the first problem that we solved is for a telecom industry. Actually, this problem is pretty generic. It exists for any services industry. So for any services industry can be seen to be organized along these 3 dimensions. The customer dimension, so you need to acquire the right customers, and you need to keep them happy. How do you keep customers happy? You need to have the right kind of products, and you need to price them at the right price point. And the processes dimension is that of defining the right kind of products, acquiring the right kind of customers, and servicing those customers using the products, or refining the products so as to keep the customers happy and the product's price point within the desired range. Now, this space is the metrics are following. I must maximize the average revenue per customer. The customer lifetime value must be maximum. The product rationalization should be only when required, and the customer churn should be minimum. So these are my KPIs. And the space itself is characterized by high dynamism, partial information, high uncertainty. Today, The way decision making happens is siloed. It is the strategies are arrived at based largely on past data, and those strategies get validated in through real world experimentation, which is time, cost, and effort intensive. The second example which I will talk about is from the societal domain, that of pandemic control. So over here, we would like to know the number of infections. We would like to know how many people need to be isolated, how many people are likely to get hospitalized, how many of these patients will advance so as to require critical care. And we would like to know, amongst the candidate interventions at my disposal, which intervention will perform best on these above four parameters. Now, this space is also characterized by high dynamism, partial information, and high uncertainty. Today, the model that is the approaches that are available work very well at a macro level, but they don't work so well on a micro level. And the statistics-based predictive models do well only for the predictions for tomorrow and day after. Any further longer term prediction, they do very badly. The third example that we use these ideas was from a cyber physical space, that of packaging industry, wherein you get the packages, and those packages now need to be sorted depending upon where they are sent. So imagine that your area of operation is divided into different buckets or zones, and depending upon the address, you now need to classify the packet for a particular zone. And so packets for a particular zone will get collected in one particular chute, and there will be people who will be emptying those chutes by loading these packages into the delivery vehicles, which will then transport them to the right zone. That's broadly the 40,000 feet overview of the problem space. And over here, your KPIs are: the average sorting time must be minimal. No package should remain unsorted, or all packages should get sorted, because if a package remains unsorted onto the sorting belt, then human intervention is called for, which is highly expensive, both time as well as cost-wise. And the number of manual interventions should be minimal, meaning it should never happen that you have assigned two people to empty a particular chute, but it so happens that the chute is getting filled up very fast, and those two people are inadequate to empty the chute. And if the chute overflows, then the entire sorting terminal comes to a grinding halt, and restarting it is again time, effort, cost intensive endeavor. So the number of outlier conditions that your system will venture into must be kept minimal. Now, this space is also characterized by high dynamism, partial information, because you just don't know what kind of packages the next workload is going to bring in. So you really don't know how many people to assign to a particular chute. You don't know what kind of a configuration of the sorting terminal you will need, which will lead to efficient sorting of the next batch. Again, the current state of practice is rely on the past data, predict as a time series prediction what the next workload would be, and then do assignment of people to chutes. And if there is any outlier condition, through seat of the pants approach, just do ad hoc interventions. The fourth example which I will talk about is from retail space, wherein retail supply chain is a supply network which starts from the factory all the way down to the local shop. And in between, you have regional distribution centers and local distribution centers. Let us look at one of the critical problems. Now, in a shop, there are um, shelves, and those shelves are stocked with the products. Uh, People come to the shop, they buy products. Uh, when they see that the shelf is too empty, then they feel that, oh, this is an old stock. Let me wait till the uh, new stock comes, so they don't buy. And if the shelf remain full and the next batch arrives, then uh, there is no inventory at a shop. So you end up losing shelf space. So therefore, one of the key problems in retail space is shop stock replenishment. Uh, and this today is done in a siloed manner. Again, based upon the past data, you say you know what was the footfall of people, you know what kind of people came in, and based upon that, you predict, uh, again, purely statistical based manner, what the footfall would be, what the composition of the kind of people entering into the shop will be, what they are likely to buy. If they buy something, then they buy something else also. Those kinds of heuristics you apply and try to solve the problem. But this just doesn't work well. So what? So these are the four kinds of problems: from information only space, cyber physical space, and societal space. And to solve these problems, what we did was the follows. Uh, we constructed a digital twin of each of these realities as a proxy of the system. We subjected this digital twin to a set of what-if scenario playing. Uh, the digital twin was synchronized with the reality in an epoch-based manner, so it was not a classical real-time in sync kind of a thing, but given the nature of the problem that we were trying to solve, that epoch-based synchronization was good enough. And we were able to significantly reduce the uncertainty in the operation of the telecom operator, the people, the authorities which were in control of the pandemic, as well as the sorting terminal thing. So the technology which we brought to the table was an actor-based digital twin, some utilities which will help you set up a simulation and visualize the results of the simulation, and some sort of high-level LTL aware language, which in terms of which you could specify the positive patterns and the negative patterns. And we build a pattern matching machinery on which will look for those patterns into the execution trace generated by the simulator. And thus we were able to state whether the goals are being met or not. Now, in the interest of time, I think I have about 15 minutes left. So in the interest of time, let me just take one concrete example. So let me take the pandemic control as an example, because I think today almost everybody amongst us is now reasonably well aware of COVID-19 pandemic. What I would like to highlight over here are peculiarities uh, of the context into which we had to solve this problem. So as you know, India is a very large country, and more importantly, it's a very heterogeneous space. It comprises of large cities, which will, like Mumbai or Delhi, etc., which is like any other city in a developed economy. But they also have places which are ghettos, very poor people. And so the country as such is a very wide spectrum of very poor, highly localities, which you will feel as if it is you are in London or New York, At the same time, there will be in the same city, there will be localities which are uh, people living in a very poor, very unhygienic condition. Now, depending upon these things, the interventions, the pandemic control interventions are going to vary. Now, if your notion, if your analysis problem is India as at a country level, then compartmental models work well. You can use those SEIR, system dynamic, etc. kind of models to figure out how many people are likely to be, how many people are susceptible, of which how many people are likely to be exposed, of which how many people are likely to get infected, of which how many people will need serious medical treatment, and how many people will just get cured. All that is possible at a macro level. And statistics based models will give you a reasonably good prediction for next couple of days. But because of this heterogeneity, macro level analysis is not good. We need a locality specific analysis and locality specific interventions. Now that's where things start getting difficult, because COVID spread depends upon the number and duration of proximal contacts that are taking place, whether what is the extent of vaccination of the population, and what are the characteristics of the virus strain, which is the current dominant strain. Please note, virus is also a temporal variable over here. And these parameters themselves are a function of what is the living area per person, what is the typical level of hygiene of the place that the person is exercising. When it comes to a place, what is the footfall per unit time, what is the typical duration wherein people mingle, etc., etc. And these parameters vary drastically. Forget about the country, even within a city, as we just now looked at. So what we did was we organized this information along 4 dimensions. First was the demographic dimension, which answers the question from a modeling perspective: who can do what, where, and when. And we also augmented information like gender, comorbidities, what is the profession, etc., etc. The second dimension which we looked at was the places dimension, which answers the question: who can congregate, when, and for how long. So over here, we modeled place archetypes, the nature of movement within these places, the nature of contacts that people can come with each other, etc. The third obvious dimension, that was of virus characteristics, wherein we modeled the spatial as well as temporal dynamics of transmission and advance of infection. And the fourth dimension was that of interventions. These were non-pharmaceutical interventions, like you are constraining movement, you are restraining the how long a place will be kept open, what would be the percentage occupancy even if the place is operational, etc., etc., and whether people should wear mask, whom should test where, etc., etc. So what we did was we came up with a fine-grained actor-based model of the Pune city. We populated it using real-world data. Now, Pune is a very large city; it's about 6 million people, just people. And if you now take into consideration the houses, the offices, the vehicles, and whatnot, the number of actors becomes really large, several tens of millions, and that would lead to a very large model. So we relied on stratified sampling so as to manage the size of the model. As regards the virus characteristics, since we are not epidemiologists, we relied solely on the information that was being published in reputed scholastic journals like Lancet, etc., etc. And we validated our digital twin by matching our predictions of number of cases, number of deaths for first 20 days. To be quite honest, we relied more on the number of deaths because we believed that that would be a more accurate parameter than number of infections, which would be a function of how many people are being tested. And in our kind of a country, which is not so well off, the testing was not 100%. So we relied on deaths. So again, just to give you a flavor of the kind of a conceptual model, what you see is a class model wherein we are trying to model households. A city is modeled as a set of wards. Ward is modeled as a set of people staying in a household and a set of places. Each place, each household, each citizen conform to a particular archetype. For place, we had 22 archetypes. For citizens, we had 14 archetypes. For household, we had about 8 or 9 archetypes, which was a represented a honest enough representation of Pune city. And then we implemented it in terms of actor types. Archetype was an actor type, which led to, through inheritance, it led to further actors, and those appropriate number of actors were instantiated and they went about doing their daily jobs. So that was the idea. So using the digital, such a initialized digital twin was then subjected to appropriate what-if scenarios, and the metrics were virus spread, the load on hospitals. We were keen on how many admissions, not just people coming to the emergency, but how many people are getting admitted. Do we see any pattern as regards age or gender or comorbidities? How many of them are likely to get advanced to a critical care? As regards load on testing, we wanted to know how many people to test, where to test, and amongst them whom to test. Should we test young people? Should we test people who are unlikely to go out, etc., etc.? And we predicted the second and third wave accurately, both as regards the onset time as well as the amplitude. We also were able to predict the hotspot localities within the city pretty accurately. And as a result, the city authorities were able to come up with locality-specific interventions. Not city-wide interventions, uniform city-wide interventions, locality-specific interventions, which led to better containment of the pandemic in our city. Plus, city authorities, as things started to unlock, they had very specific questions like, will a weekend lockdown help at all? Or should the shops on left-hand side of the roads be kept open on one day and the shops on the right-hand side be kept open on the other day, etc.? Should we allow household help to function, etc., etc.? And ability to have this kind of a digital twin helped them get a data-driven and justification-backed decisions, which, to be quite honest, was a very gratifying feeling for all of us. Because we were able to capture the demographic information, we also use this digital twin in a repurposed manner to address work from home to work from office transition of our organization. Now, what you see in front, now I really have to go very fast, apologies for that. What you see in front of you is the nature of the problem. So my organization has about 140 offices at 32 cities in India. And these cities are distributed all over, as you can see. And these cities are also quite different. Some are metros, some are not so large cities, some are reasonably small towns, etc. So the way the pandemic was unfolding over there also was very different. And then there were peculiarities, like about 40% of the employees were in a certain age range, which made them less or more vulnerable to current dominant strain out over there. Some about 20% female and 24% male associates had 0 to 10-year-old kids, and nobody knew how the virus is going to act onto the kids. And so the problem, therefore, was if we were to solve this problem using the classical digital twin method, then for each of these offices and the people over there, we had to construct 140 digital twins, which was obviously a non-scalable method. So what we did was we did a hybrid approach. So we came up with a digital twin for people and a parameterized digital twin for an office, which was instantiated very easily with the concrete data available at each office. And for the information about who is likely to get exposed, we used system dynamic or stock and flow modeling. So that's clever integration of coarse grained modeling and fine grained modeling helped us do a better job of coming up with strategies which will help our organization transition from work from home to work from office. And we did reasonably well over there. Now, in the interest of time, let me spend some more time on, while we seem to have done a reasonably good job, there are still lots of challenges which are remaining. And the challenges are along 3 dimensions: the research dimension, engineering dimension, and application domains dimension. In the research dimension, it has become now very clear to us that you cannot force fit actor-based modeling everywhere. You need a digital twin wherein you use horses for courses strategy. So we would be using agent-based models, system dynamic models, machine learned models, because all that you have is data. You have no behavior available with you. Process models or plain simple physics-based models. So your digital twin must be a multi-paradigm model. And all these different kinds of models must coexist or interoperate. How to make that happen is an open challenge. We are solving business problems, but we are relying on technical people to come up with solutions. Instead, there is a need to come up with domain-specific languages which will help intuitive and closer to problem domain specification by subject experts. So subject experts should provide just the what aspect, and from that, maybe through a successive refinement stage, probably using AI-based code completion techniques, one should be able to reach the executable specification. Today, the only way for us to validate whether the digital twin is working correctly or not is by testing. We simulate and we let the subject matter expert take a call whether what is being simulated is correct or not. Instead, we need a validation at specification level itself. And when we introduce DSLs, we will need a validation at DSL level itself, not at the executable specification level. Another big problem that we have is whenever you deliver a digital twin-based solution, it is organized along 3 dimensions. What is the domain, what is the problem, and what is the context, or for whom, which customer. Now, typically, given a problem in a particular domain, different customers will need similar solution, not exactly the same solution. So the question then is, how do you repurpose a solution that works for one context to another context? That's a big problem. Second, so far we have only addressed the problem for an island. But reality is all about ecosystems. There are multiple stakeholders, and we need to keep everybody happy. So, which means our current solution, which is encoding of Markov decision process, is not enough. We now need to evolve into stochastic games. Today, we rely on complete information. Now, we must be cognizant of the fact that the information that I have is partial and it might not be fully certain. Today, we rely on full observability. We now need to be cognizant of the fact that not everything would be observable. You might be able to observe only partially, and from that derive your KPIs. How to do that is a big problem. When you are dealing with ecosystems, you have to worry about competitive as well as collaborative use cases. In a purely competitive use case, can we aim for Nash equilibrium kind of state, which is the ideal state? If not, can we at least guarantee Pareto optimality? So these are the kind of research challenges which need to be addressed. On the engineering dimension, we need to come up with a right method, guidelines, and best practices so that subject matter experts will be able to play a more direct and uh, greater role in digital twin development. We also need very sophisticated language engineering support because we are dealing with an open-ended space. So what we need is a DSL engineering platform, so to say. The other stuff is pretty straightforward. As regards applications, we are now addressing smart cities, sustainability, letting a city authority move from fossil fuel-based transportation to electric vehicles, so on and so forth. So there are lots of open challenges. So in summary, future seems to be about large, complex system of systems that need to operate in uncertain environments. Decision making is the key. Enterprise digital twin offers a promising line of attack, but there is a lot that needs to be done. And our vision is that of knowledge guided AI native adaptive enterprise. And a book based upon this idea will out from Springer early next year. So with that, let me stop here and take questions. Apologies, I seem to have exceeded by a couple of minutes.
Thank you very much, Vinay. First, let me give you one round of physical applause.